Hey students, this is a video on advanced integration techniques. Now these are integration techniques that go above and beyond the ones that you learned in Calculus 1. So we're not just doing plain old U substitution. We're going to be taking an extra step of some kind on each type of problem. And this isn't all of the advanced integration techniques. However, these are some of the shorter advanced integration techniques. And then later on, I'll be making videos of some other advanced integration techniques, but these are all the short ones. Okay, relatively short ones. So this is just going to be a bunch of examples to try to prepare you for your homework, the quizzes, and the exam. Okay, so first example. Instructions are evaluate. Okay, and this first one you might actually already be able to do on your own, but just in case you aren't sure how to do it, I wanted to go ahead and do this one. Okay, so this first one is not too bad. This should technically be Calculus 1 stuff for you, but I'm doing it just in case you don't remember the basics of U substitution and plugging in to logarithms. Okay, so for this one, we're doing the integral. The integral from 2 to 8. The integral from 2 to 8 of 6x dx over 3x squared plus 9. Now this is definitely the easiest type of problem that shows up on your homework. So I will be trying to go through this one relatively quickly. So this one is technically just Calculus 1 stuff. It's just mostly a question of, do you remember the fundamental theorem of calculus? Okay, so what you have to do here is you have a composite function here, and so you're going to want to use U substitution, and usually, in most cases, when you're doing U substitution, you let U be the inside of the composite function. Okay, so here, the composite function is going to be 1 over 3x squared plus 9. Well, the inside of that function is this denominator here. So that's going to be U. So U is actually going to be 3x squared plus 9. Okay? So if we let U equal 3x squared plus 9, then we take the derivative of both sides. So we get du dx equals, using the power rule, we bring the 2 out front and decrease the exponent by 1. So 2 times 3 is 6x. Okay, and then if you follow my approach, I isolate dx. Okay, so here I'm going to multiply both sides by dx and divide both sides by 6x. So that's going to give me du over 6x equals dx. Okay, so we're going to plug in du over 6x in for dx. Okay, and the main reason I'm doing this problem, even though this is an easy problem, is I wanted to show you, in case you don't remember from any of my other videos, how I do U substitution. But this one is this is definitely the easiest one on your homework, because this is really just U substitution. Okay. So this one is just U substitution. So anyway, this is how I do U substitution though. So what we have is the integral of 6x times, well, plugging in for dx, we're plugging in du over 6x. Okay. And then in our denominator over here, we still have a 3x squared plus 9, but that's actually the same as u. So we have the integral of 6x over u times du over 6x. Okay, so times du over 6x. And if you do it the way I do, the fun thing about it is stuff is supposed to cancel out. So here the stuff that cancels out is actually just the 6x's. Both of those cancel out. So we're going to be left with the integral of 1 over u du. Okay, and then what's the formula for the integral of 1 over u du? Well, it's actually natural log of absolute value of u plus c. However, we're not going to be writing a plus c here because this is a definite integral, so we're going to actually be plugging in these numbers at the end. Okay? So what we've got here is the integral of 1 over u du is equal to natural log of absolute value of u, but I'm not going to write plus c because it's actually a definite integral. So, but before we can plug in the numbers of the definite integral, we have to plug in the original expression for u in terms of x. Okay, so we said in this problem u equals 3x squared plus 9. Okay, so that's what we're going to be plugging in here. So we have natural log of absolute value of 3x squared plus 9. Okay, and we're evaluating this, we said, from x equals 2 to x equals 8. Because remember, in the original integral, the limits of integration were going from 2 to 8. Okay, so those are in terms of x because the original variable was x. Okay, so we've got natural log of absolute value of 3x squared plus 9 evaluated from x equals 2 to x equals 8. So this is technically a calculus 1 problem. So what do we do at the end here? Well, we go ahead and plug in the top number into the function, and then we subtract the function evaluated at the bottom number. So we're going to have natural log of absolute value of 3 times 8 squared plus 9. That's plugging in 8 into the function. That's the top number. And now we subtract the function evaluated at 2. So it's going to be minus ln of absolute value of 3 times 2 squared plus 9. Okay? And then, 8 squared is 64. And then 3 times 64 is, 176 or something. You can use your calculator if you want to, just to make sure. So 64 times 3, 192. Well, I'm pretty bad at math, aren't I? Okay, so you got 192 plus 9. 192 plus 9 is 201. So I got ln of absolute value of 201 minus ln of absolute value of, well, let's see, 2 squared is 4, and 4 times 3 is 12. So here we have 12 plus 9 is going to be 21. So we have minus ln of absolute value of 21. Now remember, absolute value, you only need that if the number is negative. If the number is already positive like this, absolute value doesn't do anything. Absolute value just makes sure that the number is positive, but if it's already positive, you can just get rid of it. Okay, so I'm going to get rid of these absolute values. So we really just have ln of 201 minus ln of 21. Okay, and you might think that that was how you would write your answer. However, on your homework, they do one more step. So remember, if you are subtracting outside of a logarithm, that's the same as dividing inside the logarithm. Okay, so that's a trick here that we need to use. So this is going to be the same as going from left to right and top to bottom. Subtracting outside the logarithm is the same as dividing inside. So this is going to be ln of 201 over 21. Okay, and then are there any common factors for 201 and 21? Well, I can try dividing 201 by 3 and see how that goes. 201 divided by 3 is 67. So it looks like they have a common factor of 3. So if I divide the top and the bottom of this fraction by 3, on the top we said that was 67, and then on the bottom, 21 divided by 3 is 7. But then if you think about your times tables, 7 does not go into 67. So that means we can't simplify it anymore. So our answer is going to be ln of 67 over 7. And they actually put parentheses around the fraction because it's kind of big. Okay? All right, so that's the first example. Technically a Calculus 1 problem, but still good to watch in case you don't remember how to do that. So that was just standard U substitution. And you will be using U substitution for most of these integrals, if not almost all of them. But the U substitution gets trickier and trickier as you have to use more advanced techniques. Okay? So for this next example, this one's going to be a lot more challenging. This is a lot more advanced problem. Okay, so example number 2 is going to be the integral of 6x squared all over x squared plus 11 dx. Okay? And the trick with this one is just how do you do it? Because if you use U substitution, let's say you let U equal x squared plus 11, which is the inside of the composite function, then you're going to get du dx equals 2x, okay? And then if you plug that back in, things are not really going to cancel out so well. If you don't believe me, let me show you really quick. So, U substitution is problematic here. Problematic means it's not really going to work out. So for this problem, you know, if you follow my standard approach, you let U be the inside of the composite function, so U is going to be x squared plus 11. Then the problem is not everything is going to cancel out. So you get U equals x squared plus 11, so then you get du dx equals 2x. Okay, but that 2x isn't going to end up canceling out with the 6x squared. Okay, only one of the x's is going to cancel out, but the other x is going to be left there. And then you're going to have an integral in terms of two variables, which is no good. You can't do that. But anyway, if you just follow my standard approach, you isolate dx by multiplying both sides by dx, dividing both sides by 2x. Let me show you what you get. We get du over 2x equals dx. So if we plug in du over 2x, like I just said, if we plug that in for dx, something is not going to cancel out, and x is actually not going to cancel out. So our integral is now going to be the integral of 6x squared over u, because the x squared plus 11 is what we let u be. Okay, so what we have is the integral of 6x squared over u times du over 2x. So the fun thing about my method is stuff does cancel out, but the sad thing is on a harder problem like this, not everything does cancel out. So what happens here is we divide these, the x squared and the x cancel out, and you're left with an x on the top. And of course you can bring 6 over 2, which is actually 3, and you can bring that out front, which is a constant. But now your integral's in terms of two variables, which is just a mess. You can't really do anything with it. So you got 3 times the integral of 1 over u du, but then there's still an x there. So it's really x over u du. And the problem is you can't have an integral in terms of two separate variables unless it's a double integral. And we're not doing a double integral here. Okay, so your integral or your integrand must be in terms of one variable. Okay, it must be in terms of one variable only. So that's the problem here. Okay, it's actually in terms of two variables here, x and u, so we can't do it. Now, if you don't want to do long division, one thing you can try in a problem like this is you can try to plug in an expression for u in for x. Okay, so going back here where we said u equals x squared plus 11, and what we could do there is we could solve for x. So we would have x equals the square root of u minus 11. But then the problem there is you're going to have a square root of u minus 11 up here. So it's actually going to be even harder to integrate it. Okay, so what all this tells us is that u substitution fails here. Okay, and most of those problems that we do, they're set up so that they work out correctly. So what do we have to do when we're doing a problem and u substitution fails? We can't just do it directly through u substitution. Well, we're going to have to use a more advanced technique. And the one we want to use here is because we have a polynomial divided by another polynomial, we're going to want to use polynomial long division. Okay? So instead, so to simplify a polynomial over a polynomial, so one polynomial over another polynomial, we use long division. And I know some of the very fanciest calculators, particularly online, will be able to do long division for you. However, I'm going to show you how to do long division by hand so that we can actually learn it. It's really not that hard. So you're going to use long division. It's actually called polynomial long division. Okay, so how does that work? Well, we just go back, we just cross out all this stuff that we were doing when we were trying to do u substitution. None of this worked. I'm going to cross that out, cross this out. I knew it wasn't going to work right at the beginning, but I wanted to show you why it doesn't work. I don't always do that, but I want to do that sometimes. So none of this u substitution stuff worked. This is all no use. So what we have to do is polynomial long division with the original problem. Okay, so polynomial long division, your numerator is 6x squared and your denominator is x squared plus 11. Okay, so we're going to be doing 6x squared divided by x squared plus 11. Yeah, that's what we started with. Okay, and polynomial long division is a lot like regular long division. It's just you're looking at terms of a polynomial, and you just need to make sure you write the highest powers first. Okay? So for this one, looking at the highest powers, we look at the x squared and the 6x squared, and then we basically just divide. Okay? So we do this number divided by that number. Well, 6x squared divided by x squared is actually 6. So we end up with a 6 up here. Okay? So this is a lot like regular long division. It's just we're working with terms of a polynomial instead of powers of 10. Okay? So how did I get 6? I did this number divided by that number. So 6x squared divided by x squared gave me 6. So that was 6x squared divided by x squared. So the x squareds in my head, I canceled out the x squareds and we got 6. Okay, and then what do? Well, you go ahead and distribute the 6 to each of these terms. Okay, so we distribute the 6 to the 11 and the x squared. So that's going to give us 6 times x squared is 6x squared, and then 6 times 11 is 66. Okay, so we actually have 6x squared plus 66. Now remember, when you're dividing using long division, you don't add them, you actually subtract them. Okay, so this number that you get down here, you have to subtract it, just like with regular long division, but there's two terms, so you have to switch the sign of the two terms. In other words, there's a minus here, and you have to distribute that minus to each term. So that just amounts to switching the signs. Okay, so the terms were originally positive and positive, and now they're going to be negative and negative. Okay? And that's because we're subtracting. That's why you always have to distribute a minus there. Okay, and then you can just add straight down. So adding straight down, these cancel out. 6x squared minus 6x squared is 0. And then this over here is going to be 0 minus 66, which is negative 66. And because x squared does not go into negative 66, that means negative 66 is our remainder. Okay? So this negative 66 is the remainder. Okay? And then the 6 up here, that's called the quotient. Actually, let me use a different color here to make it easier. Okay, so the negative 66 is the remainder. The 6 is the quotient. And then the x squared plus 11, that was what we were dividing by. That x squared plus 11 is called the divisor. Okay, but it's easier to remember them as just capital letters. So I think of the remainder as capital R, the quotient as capital Q, and the divisor as capital D. Okay, and why am I saying all this stuff? Well, to write your answer, you have to rewrite it as quotient plus remainder divided by divisor. Q plus R over D. Okay, that's how you write your answer. Okay, so we rewrite as Q plus R over D. So I was doing Q in red plus R over D. Now the whole reason you're doing all this is because direct U substitution is not working with this problem. It's just too much. Okay, so it just didn't work, right? I mean, we did a bunch of U substitution and then we got two different variables, and so we weren't able to do U substitution. It was just too complicated for us to integrate. So that's why we're using long division. And I knew to use long division because we had a polynomial over another polynomial. Okay, so now after you've done this long division, you rewrite your integrand as Q plus R over D. So that's going to be 6 plus negative 66 divided by x squared plus 11. Okay, oops. Open up my games there. Okay, so 6 plus negative 66 divided by x squared plus 11. That is Q plus R over D. All right. And you can use an online calculator to do the long division for you, but I wanted to show you how to do it by hand because it's really not that hard and it's nice to know how it works. Okay, so what this is actually the same as our original expression. So this thing right here, the integral of 6x squared over x squared plus 11 dx, that's the same expression as this, Q plus R over D. Okay, so the original problem, integral of 6x squared over x squared plus 11 dx is going to be the same as the integral of this whole thing, of 6 plus negative 66 over x squared plus 11 dx. Okay? And yes, if you want to save time, you can use a calculator if you have a calculator that's advanced enough to do long division for you. But I think that takes the fun out of it, so I wanted to do it by hand. Okay? But now, this is something that's been broken up a bit, so now we can actually integrate this. So how do we integrate this? Well, remember, you can distribute the integral symbol when you have things added or subtracted from each other. So here I can distribute this integral to each of those terms, which is going to make the impossible integral a lot easier. Now this is something we can actually do. So we're going to have the integral of 6 dx, okay? The integral of 6 dx minus the integral of 66 over x squared plus 11 dx. Okay, so all I did there was I distributed the integral symbol. Okay, and of course you can factor those constants out front, so maybe we should do that. So for the first one we have 6 times the integral of dx. And for the second one, I brought out the minus, so I'll also bring out the 66. So for the second one, we have minus 66 times the integral of 1 over x squared plus 11 dx. Okay. Okay, so now we have two integrals, and these are a heck of a lot easier. Okay, so the first integral, remember the integral of dx is just the variable x. Okay, so for the first one, we're just going to have 6x. Okay, and then for the second integral, how do we do this one? Well, this one's a little bit harder, but if you go to our formula sheet, this is kind of in the form of tangent inverse. So if we go to our formula sheet on Canvas, hopefully you have it already printed out or on your computer, but if not, you can go to our, it's usually in the week 2 or week 3 module, depending on which course you're in. In this course it was week 3. So formulas from Calculus 1 and 2, it's a PDF. If you've watched my other videos, you've seen me refer to it many times. So I'm opening it up here. So what we're looking for is antiderivatives, because we're doing integrals, and we're looking for something in the form that we have here. So we have 1 over x squared plus 11. So I can actually rewrite that as 1 over x squared plus root 11 squared. Okay, dx. Because remember, root 11 squared is the same as 11. So hopefully now you can see that it's in a certain form. So looking at these forms here, if I zoom in, the integral of 1 over a squared plus u squared, that's supposed to say du, equals 1 over a tan inverse of u over a plus c. Okay? So the integral of 1 over a squared plus u squared du is the formula we're going to be using. Integral of 1 over a squared plus u squared du is going to equal, we said it was 1 over a tan inverse, 1 over a tan inverse of u over a. Okay, plus c. All right, but we're going to be writing a plus c at the end for all these anyway. So, so what's a going to be here? Well, a is actually the constant. So in that formula, a is the constant and u is the variable. Okay, so the order's switched around a little bit here. So instead of writing x squared first and root 11 squared second, I can just switch around the order. So I can rewrite that as root 11 squared first, and then x squared second. Okay, so here we can see that our a is actually going to be root 11. And we can also see that our u is just x. Okay, and then we don't even have to worry about du, because if u equals x, then du equals dx. So there's no surprises there. Okay, so we can actually just plug everything into this formula. So we're going to have 1 over root 11 tan inverse of x over root 11. Okay, so this right here is going to be 1 over root 11 tan inverse of x over root 11. Okay, and then we still have the 6x and the minus 66. Okay, so plugging everything in here, we're going to have a 6x minus 66 times 1 over root 11 tan inverse of parentheses x divided by root 11. Okay, and then of course, because this is an indefinite integral, we have to write plus c at the end. Okay, and that should be basically how they write their answer, I believe. Let me just make sure. Yeah, they almost do the same thing here. It looks like they rationalized the square root, so I gotta do that. Okay, so what they did is they actually multiplied the top and the bottom of this radical by root 11, so they went ahead and rationalized it. Okay, so instead of writing 1 over root 11, on my math lab, they actually write root 11 on the top and root 11 on the bottom. To rationalize it, you multiply straight across. Okay, so that gives us root 11 over 11 there. But then we still have a 66 out front. Okay, so we have 6x minus 66 times root 11 over 11 tan inverse of x over root 11. Okay, plus c. And I don't know why they rationalize sometimes and then other times they don't rationalize. They aren't entirely reliable about what they do. But this time they are rationalizing, so they're getting rid of the square root in the denominator. And then we can simplify this a little bit. We know that 66 divided by 11 is just 6. So we can cross these out. So we're just going to have a 6 in the numerator. Okay, and then what they do is they factor out a 6 from the entire expression. So if you factor out a 6, we're going to be left with parentheses x minus root 11 tan inverse of parentheses x over root 11 end parentheses plus c. So that's a more grown-up math problem with some advanced techniques. Okay? Pretty cool, huh? Okay, so that was example number 2. And let me make sure my recorder is working properly here. Okay, sorry about that. Just making sure my recorder was working correctly. All right, so what we're going to be doing next is more examples. Of course, everyone loves examples. So the one we just did was long division. And so that was number 2. So let's do example number 3 now. Okay, example number 3. So for this one, it's pretty scary, has a lot of trig functions. So this one is the integral of parentheses secant of x minus cotangent of x, okay, parentheses squared dx. So now the way this is written, you could write secant as 1 over cosine, and you could write cotangent as cosine over sine. And then you could build them, I guess, to a common denominator, but I feel like that's not really such a great way to go. So what I would recommend is that on your first step, I would recommend that you write the square and then expand it using FOIL. Okay, so we're actually going to use FOIL here. First outer, inner, last. Okay, so we're going to have the integral of, the first is going to be secant of x times secant of x, which is secant squared of x. Okay. The outer is going to be secant of x times negative cotangent of x. Okay, so we're going to have negative secant of x cotangent of x. The inner is also going to be negative secant of x cotangent of x. So those two terms are actually going to combine. Negative secant of x cotangent of x minus secant of x cotangent of x is going to be negative 2 secant of x cotangent of x. Okay, so we have minus 2 secant of x cotangent of x. And then our last is going to be negative cotangent of x times negative cotangent of x. So that's going to be positive cotangent squared of x dx. Now there are other ways of doing this problem. I'm not saying I'm necessarily doing the easiest way, but this seems to be the way that I would first think of trying to do this problem. Because U substitution can't really be done the way it was written. It's too complicated. And expanding it using FOIL lets us split it up into 3 separate integrals, which should hopefully make it easier to work with. Okay, so now what we can do is we can break this up into 3 integrals. So we can distribute the integral symbol to each individual term. Okay, and then work on these 3 integrals separately. So the first one is just the integral of secant squared of x dx. The second one is minus 2 the integral of secant of x cotangent of x dx. And then the last one is going to be the integral of cotangent squared of x dx. The integral of cotangent squared of x dx. Okay, so let's start with the integral of secant squared of x, because that's the easiest one. So if you go to your formula sheet, the integral of secant squared of u du is right here under antiderivatives on the first page. The integral of secant squared of u du equals tangent of u plus c. And that should make sense to you, because hopefully you remember that the derivative of tangent is secant squared. So that means the integral of secant squared is tangent, because derivatives and integrals are inverse operations. Okay, so this first one, the integral of secant squared of x dx, is just going to be tangent of x. And we don't need to write plus c until we're done with all the integrals, because each one will be plus c, but c plus c plus c, 3c, it's still constant, so you still just write plus c at the end. Okay, so let's take a look at this second one. Now the second integral is a lot harder, but the trick here is probably going to be to rewrite it in terms of sine and cosine. So let's take a look at this one. So we have negative 2 times the integral of, remember that secant is the same as 1 over cosine. So we have 1 over cosine of x. And then remember that cotangent is actually cosine over sine. So this one is going to be cosine of x over sine of x. Okay, dx. So the reason I wrote it that way is hopefully you can see the cosine of x's are going to cancel out. So if I cross out those cosine of x's, I get 1 over sine. And remember that 1 over sine is the same as cosecant. So you actually have minus 2 times the integral of cosecant of x dx. Okay, and then we already finished the first integral. That's tangent of x. Okay, and I like to just work on these one by one. So let's work some more on this integral of cosecant of x dx. So if we look in our formula sheet for the integral of cosecant of x or cosecant of u, that one's right here. So it's actually the integral of cosecant of u du turns out to be negative natural log of absolute value of cosecant of u plus cotangent of u plus c. Okay, so negative ln. Here we're going to have negative ln of absolute value of cosecant of x plus cotangent of x. Okay, because here our u is actually x. So cosecant of x plus cotangent of x. Okay, and then don't forget we still have a negative 2 out front. And we still have a tangent of x. Okay? Right, so then these minuses are going to cancel. So far for our first two integrals, we're going to have tangent of x for the first one, and then plus 2 ln of absolute value of cosecant of x plus cotangent of x. And again, I don't bother to write plus c until I'm at the end of the entire problem. Okay, and looking at my math lab, looks like I'm on the right track, so that's how they did it too. Okay, so let's take a look at this third integral. Now this one's tricky. This is the hardest one, so that's why I chose this one to do this one last. So for the integral of cotangent squared of x dx, you just can't do it the way it's written. It's tricky, but it's easy if you know the trick. So remember in pre-calculus when they taught you about all those trigonometric identities? Well, those are finally going to be useful now. So cotangent squared of x, if you go down to your formula sheet on the second page, under trigonometry, on your cheat sheet there, zoom in, and then looking at key trig identities, the one we want is the one for the function we have here. So cotangent squared of x, can't really integrate that by itself, but we can use a trig identity to rewrite it in a way so we can integrate it. So we know here it says that 1 plus cotangent squared of theta equals cosecant squared of theta. Okay, so we can copy that down. 1 plus cotangent squared of x equals cosecant squared of x. Okay. 1 plus cotangent squared of x equals cosecant squared of x. Okay, that's from the formula sheet. Okay, now why did I choose that one? Well, because I saw that it has a cotangent squared of x, and that's our big problem. We need to get rid of that because the way it is, if you try to do u substitution, it's not going to work. You can just take my word for it, or you can try it. But anyway, 1 plus cotangent squared of x equals cosecant squared of x. So what we have to do is we have to solve this equation for cotangent squared of x so we can plug it in. Okay, so if I subtract 1 from both sides, I get cotangent squared of x equals cosecant squared of x minus 1. Okay, so we're actually going to be plugging in cosecant squared of x minus 1 in for cotangent squared of x. And you might be wondering, well, Mr. Shoemaker, how do you know this is going to work? Well, I have a master's in math, so I know it's going to work. But what made me think of using it is cotangent squared, any power of a trig function is difficult. But something like cosecant squared or secant squared, we do have formulas for. So if we go back up to the first page we know that the integral of secant squared is tangent, and the integral of cosecant squared is negative cotangent. Okay, so that's why I wanted to rewrite it in terms of either secant squared or cosecant squared. Here it's cosecant squared of x minus 1. Okay, so plugging in here, we have plus the integral of cosecant squared of x minus 1 dx. So that's our third integral. And like I was just saying, the integral of cosecant squared of x is negative cotangent of x. Okay, so here, for our third integral, we're going to have negative cotangent of x, but then we also have to integrate the negative 1. Well, the integral of negative 1 dx, negative 1 is just a constant, is going to be negative x. So we're going to have negative cotangent of x minus x, and then of course we're going to have to write plus c at the end, because this whole thing is an indefinite integral. Okay, so if I go ahead and move this all the way down to our final answer, we've got a negative cotangent of x minus x plus c at the end that I'm adding in there. And then if I zoom out, hopefully we can see the whole thing. So this is actually exactly what they have on my math lab, which is good. That means they did it the same way. Okay, so we have tangent of x plus 2 ln of absolute value of cosecant of x plus cotangent of x minus cotangent of x minus x plus c. And that's exactly what they got. So yeah, we got it. Good job. Took a while, but we got it. Okay, cool. So I wanted to do one more example in this video of advanced integration techniques. And given how long this is taking me, I think we're going to make this be Advanced Integration Techniques Part 1. Even though I didn't write it in this title up here at the beginning of this video, I will add that in on the official title on YouTube. Okay, so this is going to be Part 1 of our Advanced Integration Techniques. So we just did number 3, I believe. Okay. And now we're going to do number 4, which is going to be the last new example on this video. Okay, so actually let me zoom back in a little bit. Okay, zooming back in here and doing problem number 4. For this one, we have a square root. Uh-oh, everyone hates square roots, don't they? Oh, my cat is breaking stuff. Oh well. Oh, never mind. He didn't break anything. He just knocked stuff over. Max, what are you doing? Okay, so anyway, what we got here is the integral of a fraction. So we have 4 minus 32x over the square root of 9 minus 16x squared dx. Okay, the integral of 4 minus 32x all over the square root of 9 minus 16x squared dx. Okay, so what is the trick here? How do we do these? Well, there's a specific trick that you want to use. You could try to do u substitution the way it's written. However, you're going to have a problem there. If you let u equal the square root in the denominator, things will just not end up canceling out with the 4 minus 32x. So you can try it if you don't believe me, but I don't think things are going to cancel out. So what you have to do instead, the trick here would be to split up the integral into 2 integrals. Now you might be wondering, well, why am I allowed to do that? Well, if you have something with 2 terms on the top, you can split up into 2 fractions. So what I'm talking about here is, here we have a 4, and then there we have a negative 32x. So I can split that up into 2 fractions. I'm allowed to do that. So that's going to be 4 over the square root of 9 minus 16x squared minus 32x over the square root of 9 minus 16x squared. Okay, and then we have two separate integrals, which are both going to be dx. So this is going to be integral of this one, dx, and then the integral of that one, dx. Okay, now you might be wondering, well, why did I do that? Why did I split it up into two fractions? Well, I have a lot of experience with these, and I know that if you go ahead and try to do the problem with U substitution, things are just not going to cancel out. You can experiment with that on your own if you want. I'm not going to take up more time on the video doing it, though. Okay, but if you split it up like this, if nothing else, it should be clear to you that these integrals are less complicated, because there's just less going on in the numerators, so it's going to be relatively easier. Max, stop it. That's my cat. He's getting very playful right now. Okay, so anyway, that's the trick, split it up. And then what do we do with each of these individual integrals? Okay, sorry about that. I had to put my cat in the other room. He's being very, very needy right now. Okay, so anyway, let's take a look at this first integral. Now, for this first integral, working on this one, looking in our formula sheet, we're looking for an integral of the form where we have a square root of something squared minus something else squared. Okay, so looking at our formula sheet, integral of the square root, so 1 over the square root of something squared minus something else squared. Okay, so that looks like the one that we were looking for here. So that one is sine inverse of u over a plus c. So we need to rewrite it in this form. So the integral of 1 over the square root of a squared minus u squared du. All right, so this one, we're going to rewrite it. We're going to bring the 4 out front. Okay, so we're going to have 4 times the integral of 1 over the square root. Well, we know that 3 squared is 9, because 3 times 3 is 9, so we can write that as 3 squared. And then what squared gives us 16x squared? Well, we know that 4 squared is 16, so we're going to have 4x quantity squared is going to give us 16x squared. Okay, so why did I write it in this form? Well, once again, I was just looking on the formula sheet for something that looked similar to this, and this one popped out at me. The integral of 1 over square root of a squared minus u squared du equals sine inverse of u over a plus c. So now we just need to figure out what a and u are so we can plug them into the formula. Okay, so here we can clearly see that a equals 3, and then u is going to equal 4x. However, we have a problem here, which is that for the 4x, if u equals 4x, then we're going to have to write in something new for dx in terms of du. So we're going to have to do that here. But that's not too hard. So what we got here is u equals 4x, so that means du dx equals 4. Okay, and then if I multiply both sides by dx, divide both sides by 4, I get du over 4 equals dx. Okay, and then we can go ahead and plug in du over 4 in for dx. And notice I'm just focusing on this first integral right here. I'm not even worrying about the second integral yet. I want to finish this entire first integral, and then we'll move on to the second one. Okay, so what we got here, plugging in, is we have a 4 out front. Okay, so we have this 4 out front, and then we have the integral of 1 over the square root of a squared minus u squared. 1 over the square root of a squared minus u squared. And then instead of dx, okay, so anyway, as I was saying, we're plugging in du over 4 for dx up here. And so we're going to have 4 times the integral of 1 over the square root of a squared minus u squared times du over 4. Again, just working on this first integral. Okay, and then if I bring the 1/4 out front, the 1/4 and the 4 are going to cancel. So we really just have the integral of 1 over the square root of a squared minus u squared du, which we just said from our formula sheet is actually sine inverse of u over a plus c. Okay, so this one's going to be sine inverse of u over a. And I don't write the plus c until the very end of the problem, because I'm lazy like that. Okay, and then, plugging back in this problem we said u was 4x and a was 3. Okay, so we're going to have sine inverse of 4x over 3. Okay, and or sine inverse of 4/3 x, same thing. Okay, so that was the first integral. Now we need to work on the second integral. And then at the very end I'll write a plus c because it's an indefinite integral. Okay, now looking at this second integral, again with my extensive knowledge of math, just looking at this, I can see that a u substitution actually probably will work here. Now what I'm looking at is the 9 minus 16x squared, I can let that be u. And then if I let u be 9 minus 16x squared, then the derivative of that is going to give me 32x, which is what I want. I mean, it'll give me negative 32x, but same thing. So that's going to mean that stuff is going to cancel out and it's going to work. Okay, but I do have to be careful here. I don't think I can let u be the square root. Okay, so if you let u be the square root here, it might not work out so well. I don't think it would work quite as well. It might not, but if we let u actually just be what's inside the square root, I think we'll be better off. Okay, so for this one, we're going to be doing u equals 9 minus 16x squared. Okay. And then taking the derivative, we get du dx equals, well, the derivative of 9 is 0. And then using the power rule, bringing the 2 out front, we get 2 times negative 16 is negative 32x. Okay. And then isolating dx, we multiply both sides by dx and divide both sides by negative 32x. We're going to get du over negative 32x equals dx. Okay, and we can just plug in the du over negative 32x in for dx right here. And I probably should have left myself more room to do this. So I'm probably going to have to erase some of this stuff. But that's okay. Okay, so we're working on the second integral here. We already figured out the first one, so we're good there. So looking at this second integral, we have a minus out front. So we have a minus integral of 32x over the square root. Well, this 9 minus 16x squared, we just said that we're going to let that be u. Okay, and then dx is going to be du over negative 32x. Okay, and then the 32's cancel out, the x's cancel out, and the minus out front is a constant that cancels out with the minus in the denominator. So those cancel out. So we just have the integral of 1 over square root of u du. And remember, the square root of u is the same as u to the 1/2. So let's rewrite it as u to the 1/2 power down there. And then if I move that u to the 1/2 up to the numerator, then I can use the power rule. Okay? So I actually have, let me move my second integral over here. So what I actually have there is positive integral of u to the negative 1/2 du. Okay? Positive integral of u to the negative 1/2 du. Okay, so what do I do with this one? Well, now it's actually easy. Now I can just do the power rule. So remember, the power rule for integrals is the reverse of the one for derivatives. So instead of subtracting from the exponent, you add to the exponent, and instead of multiplying by the old exponent, you divide by the new exponent. So in other words, we just go ahead and we add 1, so we get negative 1/2 plus 1, and then we divide by the new exponent. So we divide by negative 1/2 plus 1. Well, what's negative 1/2 plus 1? That's just 1/2. So here we're going to get u to the 1/2 divided by 1/2. Okay? U to the 1/2 divided by 1/2. And, okay, so we got u to the 1/2 divided by 1/2. And remember, 1 over a fraction is the same as multiplying by the reciprocal. Okay, so if we flip over the 1/2, we're going to have a 2 on the top. So we're going to have 2 times u to the 1/2. Okay, 2 times u to the 1/2. And then our u for the second integral, we said was actually 9 minus 16x squared. So we have plus 2 times square root of 9 minus 16x squared. Okay, so I went ahead and replaced that 1/2 power with a square root, and I plugged in for u. For the second integral was 9 minus 16x squared. Okay, and then of course we need to combine this with the first integral, which was sine inverse of 4x over 3. So bringing this one over here, we've got plus our 2 times the square root of 9 minus 16x squared. Okay? And then, of course, at the very end, because this is an indefinite integral, we don't plug in any numbers, so we just go ahead and write plus c. All right, so that's going to be our final answer. Sine inverse of 4x over 3 plus 2 times the square root of 9 minus 16x squared plus c. And that's